Okay, any questions? Right, it's on Friday, noon to 2 p.m. Even you cannot come to the whole time, please still try to come for the food and then leave. No. Okay, so what did we study last time? We talked about the cascode stage, right? Do you still remember cascode? We need to distinguish cascode from cascade, right? Cascade is just like, this is a common source amplifier. Its output go to the gate of the next stage, and the drain go to the gate of the next stage, just like a domino, right? You push it one stage to another stage. This is also, you can treat like that, but we want to look it in from another perspective. So the cascode is that I stack two transistors on top of each other, right? So this is the source, and this is the drain, right? And then you stack that. Why do we want to do that? Because we have learned about common source with degeneration. And what is the purpose of common source with degeneration? Do you remember? What's so special about common source with degeneration? Say again. You have a lower gain. You are right. But okay. So yes. Good. Sorry. Let me summarize it. You are right. I was not thinking in that way. Common source with degeneration, you get lower gain because of negative feedback. So we have all the benefits of negative feedback circuit, like more linearity, less sensitive to variation. Very, very good. That is right. But then what do you say? Okay, that's what you more control. Very good. Yeah, but that's not I'm trying to fish for. Yes, but that is correct. You are absolutely correct. That is the main purpose of common source with degeneration. What I'm trying to say here is that you also get a larger output impedance in this perspective, right? And then what is the output impedance? It is R01 times 1 plus GMRS, right? So we want to increase the output impedance of the circuits because we want to increase the gain. What is the gain of any circuit? Do you remember? Yes, it is V out over V in, but in terms of the two important quantity we discussed last time. Very good. Overall GM times overall R out, right? I missed something, right? What else do I miss? Negative. Excellent. Yeah. So always remember this. But this GM is the overall GM, not just the GM of the transistor. Although last time I showed you that for common source, the capital GM is just the small GM of the transistor, right? And then R out is the overall output, right? So the reason that we want to increase the output impedance in this case, just for this case, is because I want to increase the gain, right? So last time we say that then the output impedance of a cascode circuit is equals to this. That is because I can treat this one as the degeneration transistor. And then when I look down, this is RO2, right? So I replace RS by RO2. Then I will get a gain, which is approximately R10 multiplied by GM1RO2. So originally, it is only originally it is only R01, right? When you have the just common source. When you just have the common source, when you just have the common source, you have R01. But because of this degeneration, is amplified by GM1RO2, the output impedance. Is this okay? Any questions? Okay, if no, then we will just quickly use the same methodology or the same view, right? I claim that this is a PMOS cascode stage. Do you agree? Let's start with what we always say. This is PMOS because the symbols tell me that it is PMOS, but where is the source and drain? Source is at higher potential, right? Drain is at lower potential. This is a higher potential. This is at lower potential. And then I also know that this is constantly biased, so this is AC ground, right? If you still don't see it, on the top right, you see I have the cascode circuit for NMOS. Again, this is source, this is drain, this is source, this is drain, and this is AC grounded. Make sense? Now, if you look at topology, imagine you are the current, you are the hole or electron. You stand here. I go from here, drain, and then this transistor gate grounded source, and then drain of another transistor gate grounded source, and then ground again, because this is VDD AC ground. If I come to NMOS, I go down again, drain, source, ground. If you really spend the time to draw the small signal model, you will find that you get exactly the same result, because you solve exactly the same set of equation, right? So naturally, I will know that this output impedance must be the same as what I learned earlier. Based on this circuit, I know that this output impedance, right, if you forgot, is equals to R01 1 plus GM1 RO2 plus RO2. What would be the output impedance of this one then? He said RO1 times 1 plus GM1 RO2 plus RO2. Do you agree? You think it is reversed? Then let's see what we did here. So we have R out here. What I see is M1 and then M2. And then my solution is RO1 times GM1 RO2, right? How about this one? What do I see first? M1 and also M2. So the sequence is the same, right? So turn out that it happened that they are the same. Okay, so this one you need to be very careful if you decided to borrow any equation from the cheat sheet. Any questions? So I give you 2 minutes. Okay, and I already told you that the output impedance of NMOS cascode, if this is M1, this is M2, is RO1 plus GM1, not GM2, RO2 plus RO2. Now I given this circuit, what is the output impedance of this circuit? Right? You need to think about the small signal a little bit when you look at this. I'm not blocking you, right? I don't think I'm tall enough. RP, yeah. So turn out that it has a parallel resistance due to whatever reason, maybe manufacturing problem, right? It can be a defect or someone put it deliberately. What would be the output impedance? Right? And you know the trick of this class. I give you 2 minutes, then it means that this one should not require to solve any small signal model. It must be inspection and then map it to whatever we have learned. And naturally, I gave you this, it must be related to this equation, right? So a hint is that how is this RP related to R0, R1, right? If we draw the small signal model. And then if we can combine them, then maybe, and then you realize that you might be solving the same equation, then you can do some substitution. So, yeah, and feel free to discuss. Yeah. Discuss with each other. I think discussion is good for you to understand. Anyone already have an idea? You have? Good. Okay. Then anyone want to teach us how to do it?
R01, but a parallel RP.
Okay, he said, okay, the answer is correct. Everywhere that you have R1, you do a parallel to RP. Okay, anyone want to explain why he's correct? Yes, please.
Because the M1 component is R01 for RP has to be parallel to R01, so it's a parallel to one.
Okay, excellent. So he's saying that because RP is, so I don't know how to repeat what he said, I'm too slow, but then now I will explain. Now, if you draw the small signal model of M1, right, you assume you draw everything, but I only need to zoom into M1. GM1, VGS1, you will get R01, right? And then you have other parts, correct? And when you don't have RP, you will get this equation. But now if you have RP, then let's say you cannot see it, naturally you are going to just draw the RP and you realize that this RP is just in parallel of R01. So I can represent this whole thing by R01 parallel RP. It's just a name. Now it's called R01 parallel RP. Then if you try to solve the KCL, KVL again, you should get the same result, except that R01 become R01 parallel RP. Is this okay? Yeah, thank you very much for the answer and explanation. So the result is R out equals to R01 parallel RP times 1 plus GM1 RO2 plus RO2. I only need to change RO1. Okay, clear? And this is rigorous. This is complete. Okay. Okay, so now let's start looking at the cascode circuit. Now be very careful. A cascode circuit, as what we said, we stack two transistors together, but the input goes into the bottom transistor, not the top. If you go to the top one, it becomes a common source with degeneration. Okay, the inputs goes to the bottom. And why do we do that? Let's do it step by step. First, how do we find the AV, the gain? We already just say that AV equal to negative capital GM times R out, right? Again, GM is the GM of the whole circuit, and R out is the R out of the whole circuit. Let's find the GM first. This is a little bit difficult. What is the definition of GM? Do you remember? Excellent. Current over voltage. Which current, which voltage? Excellent. Under what condition? Do you still remember? V out is 0 when V out is grounded. Okay, so here I'm going to follow what you said. I'm going to ground the V out, and I'm going to measure the output current. Remember, by definition, I out is going into the circuit. Okay, I need to ground the VB1. I need to ground VDD. How should I treat the constant current source? I1. I'm doing AC signal. Open it. Right? Because it's constant current means there's no small signal current. Then in small signal means it's infinite impedance, right? So you open it. And of course, I out, then where will I out go if I open the top? It will all go to here, right? Now, where does this current go? No other place. And if there's no channel length modulation, it's going to go here also, which is equal to ID. Okay? Do you agree? Basically, I'm saying that if I grant the output, any currents, and then because of this perfect loading, infinite impedance, all the AC current will go down, right? So this is ID. And it is also ID1. How about VI? What is VI in this case? V input. In terms of the source gate drain, what is that? VGS, which transistor? 1 or 2? 1. Do you agree with what he said? The input is VGS1, right? Because this is the input. This is VGS1, correct? Okay. Then the problem becomes the overall GM of the circuit is equal to ID1 divided by VGS1. What is this quantity? ID1 divided by VGS1 of a transistor. It's just equal to the transconductance of that transistor, right? By definition. This is just equal to small GM1. Is it negative? Now then you need to think about the definition, right? The definition is that if the current goes down ID, right, it is called GM1, so it's just positive. Or you think of this way, when VGS increase, ID will increase in this direction by definition, right? So it is still GM1, okay? And is that okay? Is this clear? Very fast, not simple, but very critical. You use a lot of important concept here. Definition of GM, you need to short it. And then you need to open the current source, short the constant voltage. And then you understand that, oh, this current is flowing all the way down when there's no channel length modulation. Because if you draw the small signal, you will find that this won't be the case when you have the channel length modulation. So this is a good approximation. And then finally, you see, as long as I deduce it to ID and VGS, I really don't care what else is outside. It becomes just a transistor. It's asking me what is the change of ID as a function of VG. Because ID is fully controlled by VG when there's no channel length modulation. Make sense? So that's why this is GM1. Okay? So I got the capital GM already. Then my second thing I need to find is what is R out. And you learned that already. R out equals to what? What is the definition? V out. I out when V in is 0. Thank you. Right? So I try not to draw here, but if I do that, again, I need to open the current source because it's small signal, right? So this is what I have. This is grounded. This is grounded. And then I look at the R out. This is I out, and then this is V out. Is this okay? Why this is grounded? Why M2 is grounded again? The gate? Constant B1. Very good. Because it is a small signal. Why M1 input is grounded? Gate? By definition. And now you look at this. I really don't care what you call this cascode or whatever. But after it is grounded, this is just what we have learned before. Right? For common source with degeneration, for and here cascode or whatever you want to call it. This is this equation we have been using because both of these are grounded, right? By definition. So from here, I know that this is RO2 times 1 plus GM2, RO1 plus RO1. Why I have GM2 instead of GM1 and RO2 instead of RO1? Because the top transistor, which is closer to the output, is called M2. Okay? The reason I have RO1 GM1 is because this is called M1. Is that clear? Yeah? So I have this, but I will do some approximation. Again, I say this is approximately equal to RO2 GM2 RO1. Yeah. Only when we compute the GM, right? So because if I claim there's no channel length modulation, then it will be infinite output impedance. Yeah. So again, right? So in engineering, you need to do different type of approximation at the right time. This is the difficult part. Okay. So what is the total gain now? AV equals to negative GM R out, which is equal to negative GM1 RO2 GM2 RO1, correct? I just combine them together, right? Which is just equal to, if I assume GM1 and GM2, they are similar. They are similar actually, because transistor size will be similar and they have the same current bias, right? And you know the currents determine the GM, right? This is like GMRO square, just an order of approximation. How is this compared to the gain of a common source? What is the gain of a common source? Yeah, and let's ignore RD because now we are using an infinite load, right? So it's just GMRO, right? This is the square of it. So if you had 10 for your common source amplifier, you get 100 for Cascode, right? So this is how you increase the gain a lot. So Cascode amplifier is used a lot in the applications. Okay. So here I want to emphasize two things. Why we don't apply the input to M2? Right? Why? Of course, by definition, Cascode is like putting at the bottom the input, but we could have applied to the top transistor, because if we apply to the top, the GM is just the GM. It becomes what type of circuit if I apply to the top? Beyond common source, and is it only common source? With degeneration. The GM, it becomes GM1 divided by 1 plus GM1 RO. Not GM1, I mean GM2. GM2 RO 1 GM2. Right. So it is going to reduce by GMRO, right? So it's reduced when you multiply them together, they got canceled. You don't really get extra gain. Okay, make sense? If you remember, RO1 is just like RS, right? Then while your output impedance increased by so much GMRO, your input impedance, right? This is like approximately GM2 divided by RO1 GM2, right? Your output impedance reduced. I mean, your output impedance increased, but your transconductance reduced, so they got canceled. Okay, is that clear? Now, so a little bit confusing, right? But I just want to say we have been using common source with degeneration to explain that the output impedance is going to increase. But eventually, the Cascode actually has the input applied to the degeneration transistor of a common source amplifier. It's just a way to, just do not get confused, right? So if this is confusing, just The point is just remember that the input to a cascode must be at the bottom. Otherwise, you become a common source with degeneration. Okay, then you do not get the gain you want. Okay. Any questions? Okay. If no, that is good. Now I improve my amplifier a lot. I increase the output impedance a lot. The problem is, how do I implement this current source? Right? How do I implement this current source? For this one, for the left one, right? I already say that the gain equals to, maybe I'm not going to talk about the gain. Let me only talk about the output. The out equals to RO2 times 1 plus GM2 RO1 plus RO1, which is approximately, right? Besides the full equation, I want you to be able to do the approximation also. Equals to RO2 GM2 RO1. Is that okay? That is the output impedance. Why I say that? Because when I go in, this R out equals to R up parallel R down. Right? And R up is infinity. Right? So good, because R up is infinity, I basically get a very high gain, right? But what if now I want to really implement this circuit? There's no real ideal current source, right? That is just a pen and paper. In reality, how about I implement the current source by using this? First of all, is this a good current source? Do you remember? What is this transistor? And PMOS? Where's the gate? Where's the drain? Where's the source? Top, source on top, right? So what is the input impedance when I look into here? RO. Yeah, whatever number it is. RO. Are you okay? Because I look into the drain, right? So what will be the output impedance now? It will be R up. Let me call it P, okay? Parallel whatever is below. Right? Do you agree? Because whatever looking down is the same as this one, right? Which is R02 GM2 RO2, which is very large. But when I look up, what do I get? ROP. Which one is larger? The last one is much larger, right? Looking down is much larger, right? And then I have a small one. Maybe this one increased by 10 times. This one is still the original value, right? Then what do I get? The small one will dominate in a parallel circuit, right? Then my gain is not going to be high anymore. Because what is my gain now? Is equal to negative capital GM R out, which is negative ROP times GM1. I have the gain the same as the common source. Right? So my point here is to show you that even you have a very high output impedance for your cascode, if your loading has a low input impedance, you are going to screw up. And this is easy to understand. Just think about when you have a common source. I just call this RD. Right? The gain is negative GM RD parallel R0, right? Even you have a very large R0, if your RD is lousy, you actually get negative GMRD only, right? You make your R0 very large, infinity. So what? The gain is still negative GMRD, right? Same in this case. Now you make the bottom, the R down very large, but the loading is very small. Then it's dominated by the loading. As a result, you get AV equal to negative R0 P parallel GM. Again, R0 GM. You get the gain, which is the same as the common source amplifier, right? Same order of magnitude. Is that okay? Any questions? Is this clear? Any questions? Okay. So if that is the case, how do we solve the problem? It's nothing difficult. It's just that then for the loading, let me use the cascode also, right? So on top, if you read it carefully or look at the bottom first, this is drain, this is source, this is drain, this is source. Looking up, this is drain, this is source, this is drain, this is source. Again, it is cascode, right? Because we're going to ground it, right? This is a constant voltage. So naturally, R up is just the same. You still have RO3, GM3, RO4, right? I use the simplified one, okay? And how about R down? Okay, somehow here we call it, instead of up, I say OP, so I just call it OP. Here I call it ON. This is, can you tell me what is the input impedance when you look down, the RON? RO2, GM2, RO1. They have the similar magnitude, right? So the output impedance is equals to RO3, GM3, RO4 parallel RO2 GM2 RO1, which is large because both of them are large, unlike this case. Okay, this may be 1 kilo ohm, this is 10 kilo ohm. Now this become also about 1 kilo ohm. But this is 10 kilo ohm, maybe 5 kilo ohm. I only reduce it by half. Yeah.
In this case, we can simplify.
Simplify what? Okay, here is not really simplified. Let me emphasize. I don't simplify. I just claim that they have similar magnitude, and then I call it GM. Just an idea. Say, oh, this is just transconductor times RO. So you don't simplify. This is not really a simplification. I just yes. Yeah. Approximation. Yeah. Provided that maybe I just be careful. I just say assume GM1 is similar to GM2 and we call it GM. RO1 similar RO2 and we call it RO. Okay. So here, yes, so you can do something similar. Then you say it is half RO square GM. Yeah, you can say that. Yeah. Okay, good.